So I want to start by focusing in on some of these algebraic properties of vectors, and I want to use this as our opportunity to do our first proofs of linear algebra. All right, so I'd like to prove two of these. The two I'm going to prove are this one and this one. So the first property is that u plus v equals v plus u. So notice that I've started the proof of the first one, and I've done it with three different lines. So I've got a claim line, followed by a proof line, followed by sort of a let line where I define a few things. And that's going to be not every, but almost every proof that you do will start in a similar manner. So we said let u and v in Rn be given. And so now let's see if we can clarify what that means. So this implies that there are u1 all the way to un, and these are all scalars, and v1 all the way to vn in R. So these are real numbers such that, and so then we have u, hey, go away, such that u vector equals u1 all the way to un, and v equals v1 to vn. Looks like I'm going to need a little bit more space. Remember, what we're looking at is, our claim is that u plus v equals v plus u, and we're going to treat this sort of like we did with trig identities. And so we're going to start on the left side and try to get to the right side. So this tells us that u plus v equals u1 to un plus v1 to vn. And then you've used vectors in the past. What can you do when you have two vectors written as components? Yeah, you can add the components. Thank you, Ben. Thank you, Felix, for that. So we can add the components. So this tells us that, or this is equal to u1 plus v1 un plus vn. What good thing can you do once we have this written in terms of components? So we've added the components.
Can I resolve it?
We can, so at this stage, maybe it helps to go back and think about what we're trying to accomplish. What we're trying to accomplish is we're trying to reverse the order. And so now that we know, now that we broken it into a whole bunch of numbers, now we can use some of our old number logic and we can just reverse the order of those numbers. So we could write this as v1 plus u1 all the way to vn plus un. Split it apart into components, or like we have a sum inside the vector, and so now we could split it up into the sum of two vectors again. We have v1 to vn plus u1 to un. Good news, this is equal to v plus u. Trying to shrink it down. So there's the whole thing. We have one more step to do at the end. And so our last step is going to be to state our conclusion. We would say something like, therefore u plus v equals v plus u. Let's do a second one. So let's prove V. So we're going to start by writing down our claim. And so our claim is that C times U plus V equals CU plus CV. So then that's our first line that we have. Then our second line is we write the word proof, underline it, we put a period. Third thing we do is we start with our lets and we start with our proof. So in this case, you'll notice that there's a C given and a U given and a V that are all showing up in that claim. And so we will say, let scalar, which just means number, C, and UV in Rn. So if U and V are in Rn, those are given. This tells us that there are U1 to UN and, oh, that's a terrible, it's even bad ampersand for me. And V1 to Vn in R such that U equals U1 to UN and V equals V1 to Vn. So we're going to go back. So we've defined all of our terms, and then we look back at our claim. And just like we did in the previous, we're going to start with the left side, and we're going to work to the right side. Thanks for the suggestion, Twee. So if I have C, so this would be equal to C times U1 to UN plus V1 to Vn. So we're trying to get to Cu plus Cv. So we're going to again add our U and our V vectors together. So we have C times U1 plus V1 all the way down to UN plus Vn. This is going to be, just using your old vector rules, this would be like multiply the constant by each component, distribute it out. So now we're using the properties of arithmetic to do the distribution. So we're not using vector quantities or properties. Now we have two vectors being added together, so we have a sum inside, so we can split it up. Now we can take our C's out. And we're just about there. Good news. This is equal to Cu plus Cv. Are we done?
We need to say therefore.
Exactly. Thank you, Megumi. So therefore we have our C of U plus V equals Cu plus Cv. Gets a little small when I zoom out so you can see the whole thing all at once. So let me make sure it's clear what the point of all that was. Purpose of doing those proofs wasn't because we were concerned about vector principles or properties. The purpose of the proofs was to show examples of how we will do proofs in this class. So it's trying to give you a model for what we're going to be doing over the course of the quarter. And there will be other formats, but the one we just did was one of the most basic. So let's move on, and we're going to talk about a concept here that is a big deal. So this concept here of a linear combination is a big deal. And basically what it means is that you have a whole bunch of vectors, all these vectors, and then you have a whole bunch of scalars. So you've got these scalars, and so notice you've got all those vector times scalar is showing up here. Vector times scalar, vector times scalar. So let's look at this in a graphical sense. So if you have, I'm trying to figure out which color to use, sorry. You have V1 is negative 1, 1. So here's your V1 right here. You can see that here would be 2V1, 3V1, 4V1, et cetera, et cetera. You could have V2 be 2, 1. So here's 1V2, 2V2, 3V2, negative V2, negative 2V2, et cetera, et cetera. And so you can imagine trying to locate a point. So if we go trying to locate this point over here, we could ask ourselves, how many blues and how many yellows do we need in order to get there? Well, it looks like we're going to need 3 blues. That's 3 V1s. And then it looks like, well, I guess you could do it this way. Minus 2 V2s. Oh, writing in yellow doesn't work very well. Equals U, something along those lines. So the main thing that I want to point out to you here is that these vectors, they form a new type of graph paper, a parallelogram grid. So our new word, our new phrase, if you will, is the phrase linear combinations. And you can visualize linear combinations as giving you ways of finding things on kind of these new parallelogram graph papers or grids. All right, so in example 4, we want to determine whether B can be written as a linear combination of A1, A2, and A3. And so you might be tempted to try to create a parallelogram grid, but if you're trying to create a parallelogram grid, the issue is that these vectors are in 3 dimensions. And so you'd be sort of needing 3-dimensional prisms potentially, and those would be hard to draw. So we're not going to do this graphically. So let's see if we can unpack it, trying to make things work better for you. All right, so let's think about this one as the pink one, and this one, the yellow one, and then we've got a green one here and blue one here. And so let's see how this works. So if we're trying to decide whether B can be written as a linear combination of A1, A2, and A3, what we're asking is, are there constants? Are there C1, C2, C3 such that C1A1 plus C2A2 plus C3A3 equals B. Something like that. And again, here's your A1, your A2, and your A3. Okay. So to figure this out, we need to solve for whether we need to solve C1, A1, which is 1, negative 2, 0, plus C2, 0, 1, 2, plus C3, 5, negative 6, 8, equal to 2, -1, and 6. So now we should be able to combine all this stuff into a single vector on the left. So this would be like saying you have like C1 minus 2 C2 and 0 C3 plus C2 2 C2 plus 5 C3 6 C3 plus 8 C3 equals 2 minus 1, 6. And I'm hoping, let's see, from Felix. So I'm hoping that everyone sees that this sets up a system of 3 equations and 3 unknowns. And so we can solve this using a matrix. I'm hoping you see that this gives you 1, minus 2, 0, 0, 1, 2, 5, -6, 8, and then 2, -1, 6. Like that. People see the connection? And so, good news, we can now use you've done all the hard work, so now let's use our Texan friend. And in case you're new to me, Texan friend is what I call your graphing calculator because they're Texas Instruments. So if you did the RREF on this thing, what do you end up with? I've got my Texan friend. So I use my Texan friend and I got 1, 0, 5, 2, 0, 1, 4, 3, 0, 0, 0, 0. Let's make sure that we see what's going on color-wise. Notice that let me get that in a second, Malcolm. So notice that the A is just your first column, B is your second column, C is your third column, A1 is your first column, A2 is your second column, A3 is your third column, and B is on the other side of the augmented matrix. No, you're good. From Gerald, yes, 1 free variable. Let me go back to Malcolm's question. So when should you use your calculator? 1.3 and beyond, unless told otherwise. Gosh. Yep. As much as possible. Yep. Good question. All right, let's make sure that we understand what this is saying. So this first column represents the C1s. Represents the C1s, then the C2s and the C3s, and then this is what it equals. Yeah. Well, it's not so much the use of paper, it's the fact that we make so many mistakes that makes row reducing by hand such a pain. So what this is saying is it's saying that C1 plus 5 C3 equals 2. Saying that C2 plus 4 C3 equals 3. And then C3 is our free variable. Okay. And so we can put that stuff together and we can say that C1, C2, C3 write, if it's free, can we write C3? Yeah, yes, from Ben. You could also write or C3 equals C3, something along those lines. Or you could just put, C3, leave it on its own. Yeah. So we're saying it's going to be equal to 2, 3, 0 plus C3 times -5, -4, 1. And like Felix said, you could also write C vector over here if you wanted, but at least in the early days, I think you will find it helpful to write it this way because it will remind you of what you're doing. In time, you'll definitely be able to write less. And notice it's negative here. And the reason is because imagine taking that 5C3 and moving it to the other side. And taking that 4C3, moving it to the other side, which is why you'd have a -4 there. Questions? All right, let's go back because I'm not sure you know what we've actually just did. So if you go all the way to the top, the question was determine whether B can be written as a linear combination of A1, A2, and A3. And so the answer to our question, so if this is our question right here at the top, the answer to our question is yes. Yes, it can. For example, we could say that B is equal to, what was that? 230. It would be equal to 2A1 plus 3A2 plus 0A3. You might ask, where did those come from? This 2, 3, and 0 are the same 2, 3, and 0 I found right here. And so yeah. Questions? There's an infinite number of answers. Yeah, from Ahmed. Yeah, that's exactly right. There's an infinite number of answers. So you could let C3 be 1. You could let C3 be 2. You could let C3 be 4. I just happen to choose C3 equals 0 to make things easy, like Gerald said. So there's an infinite number of answers. I just listed 1. Okay. Other questions or clarifications needed? No. From Ahmed asks, so C1, C2, and C3 can be anything. No, they can't be anything. They have to be of this form. C1, C2, C3 of this form. Let's keep going, see if we can get a little bit farther before we go to our beautiful 3-day weekend, remembering Martin Luther King Jr. and all those that gave so much for civil rights. From Calvin, an infinite solution since you have a free variable, right? That's correct. There's an infinite number of solutions. So this now gives us a way of seeing a connection. So if you look at this vector equation up top, you'll notice that it's the same form as the thing that we were talking about before, where here's our A's. Make sure my colors match. Well, somewhat. Here's your A's. And there's your B. And your B ends up being the end column in the matrix. And your A's end up being the earlier columns in the matrix. And then you can row reduce to find the x1 to xn. So here we RREF to find x1 to xn. So this is sort of like the general form of the question that we just did. So if V1 to VP are in Rn, then the set of all linear combinations of V1 to VP is denoted by span. So span is the set of all linear combinations. And it's called the subset of Rn spanned or generated by V1 to VP. That is, the span of V1 to VP is the collection of all vectors that can be written in the form C1V1 plus C2V2 plus ... plus CP VP, where C1 to CP are scalars. So let's see if we can track what this means. So for example, when we say that B is in the span of V1, V2, all the way to VP, I think there's some comma stuff that's wrong, comma. This means that there exists scalars C1 to CP such that B is equal to C1 V1 plus ... plus CP VP. Okay. Or you could translate this phrase, if you want, to mean that B is contained in the span, or B is an element of the span. It's kind of a new vocab. We'll be using it a whole bunch. Don't worry if it's not 100% clear yet. But questions so far? Every scalar multiple of an individual vector is in the span. Okay, so this guy right here is in the span. And this is true since CVK equals 0V1 plus all the way to VK minus 1 plus CVK plus 0 VK plus 1 plus ... plus 0 VP. So what's important to note here is that you have a linear combination of all the V's. So here's your scalar times all of those V's, but all of the scalars are 0 except for the all-important, I think sometimes the ... dots and all that can be hard. So these are here, this stuff, this is all before K. And these ones would be all after K. And then here's the kth term. So moral of the story is that every scalar, like the point of this is that that every scalar times a vector is in the span where we include that individual vector. So let's talk geometrically about span. So here, if we're looking at the span of V, and our V is just right here, so then the span of V would be everything that's on the line. Span of one non-zero vector is a line. And I put the line in quotes simply because we could be in 5 dimensions or 50 dimensions or something like that, where the concept of a line isn't quite as clear to us. Megumi asked, could I explain once more why the scalars are all 0? So I think this is a reference to up above. So here we have that the let's see if I can make it clear. We have that CVK is in the span. So what that means is that we can make CVK out of V1, V2, V3, all the way to VP with a linear combination of them. And so our question is, how much of V1 is there? How much of V2 is there? How much of V7 is there? How much of VK is there? How much of VP is there? And so in order to see that to make this happen easily, at least, we'll say we've got C, VK, like those are going to match. And then we don't need anything else in order to make this true. And so we're going to get rid of all of the other vectors in that spanning set. So we have the zeros all the way along because we don't need anything else in order to make the CVK. Good question. Thank you. Any other questions so far? All right. So in this second little drawing, if we want to look at the span of VUV, you could imagine having a U vector and a V vector, and the span of those would be all the vectors on some plane that includes U and V. So assuming that U and V are not parallel, assuming U, V not parallel, their span is a plane. From Seche, if they were parallel, would their span just be a line? Correct. So let A1, A2, and B be as given. And we want to ask, is B on the plane or on the span? Question for you. I have a little box here. Do you guys have a box, or did the R print for you? Does it print right for you?
Yeah, it's an R.
So the R prints. So for those of you that got the printed versions, it's an R, and those of you that got the downloaded it, you got a box. Is that correct? Okay. All right. Very good. Well, sort of very good. So this would be R3. That's what that is. The span of A2 is a plane. You can, first of all, you can see that these two vectors are not scalar multiples of each other, i.e. they're not parallel. So if you look at the first component, you have 1 and 3. So you'd ask, is the second vector 3 times the first? And then you look at the second component where you have 3 and 10 is not 3 times 3. So you know that they're linearly independent. So if we want to know, so we have that the span of these guys is a plane, and we want to know, is B in that plane? So to figure this out, what we can do is we can row reduce. So what we can REF, the augmented matrix, when we row reduce this, we get out 1, 0, 0, 0, 0, sorry, 0, 1, 0, and 0, 0, 1. And you might be asking, why is it that we can do this? Because we're asking, here's the context. C1 times 1, 3 minus 2 plus C2 times 3, 10 minus 4 equals -1, 4, 2. So we can solve this system right here with the row reduction. Where notice A1 becomes your first column, A2 is here, and A and B. So question is, what does it mean? So what is meant, how do we interpret this row reduced matrix at the end? Oh, from Andrew, it's no solution, right? Because of the third row being 0, 0, 1. So like Andrew says, if you focus in on that last row, this tells you that 0 equals 1, which tells us that the system is inconsistent. Or in our case, the question was, is B in that plane? Or so we would say B is not in the plane. So the next question is a little bit similar. So it says, let V1 equal 1, 0, -2, V2 equals -3, 1, 8, and Y equal H, -5, -3. And so the question asks, for what values of H is Y in the plane generated by V1 and V2? So if you put it in context, in the previous question, we were asking ourselves, is B in the plane? And it was not. And in this question, we're basically asking, is there something, what would we need to do in order for this vector to be on the plane? So we're trying to figure out. From Ahmed, asking about the plane, and Hui, that's dead on. So the yellow and the green vectors do form a plane. It's just that the blue one is not on it. It's somewhere else. Graphically speaking, we're saying it's like in this picture where you have U and V are on the plane, but the X vector is not on the plane. This would be like what we had in this last one. Good question, Ahmed. So for what values of H is Y in the plane generated by V1, V2? Well, we got to start by setting up a matrix, just like we did in the previous example. So the vectors form the columns of the matrix. And we need to row reduce. So anytime you have a letter in your matrix, you can assume that I'm asking you to show me the steps, to not use technology to do the row reducing. You can check by hand if you want, or you can check with technology if you have that, but just assume that I'm asking you to show the steps. So I want to eliminate the -2. So I have row 3 plus 2, row 1 goes to my new row 3. Now I'm going to have h, -5, and -3 plus 2h. So we're approaching the row reduced form, but we're not quite there yet. So let's see, what did we do? We took that -3 and turned it into a 0. Now we need to take on that 2 and try to get that 2 to be a 0. So we'll have row 3 minus 2, row 2 to row 3. So let's see. So what does this mean? Our question asks for what values of h is y in the plane. If we want to know what values of h is y in the plane, then that means we want this to be consistent. In order for this to be consistent, what must be true about this last row down here? This one?
It has to be 0.
It has to be 0, exactly. So we need 0, 0, 0 right here for that orange row. And so we can solve 0 equals 7 plus 2h, or get that what h equals -7/2. So this tells us that y is on the plane if and only if h equals -7/2. IFF, you guys remember what that means from somewhere else? Yeah, from Ben. Yes, I saw lots of notes in the chat. I missed those earlier, so good call from all of you. So IFF is if and only if. And we'll use that throughout this class.